Welcome to lecture 19. In this week, we are talking about basic concepts of optimization part 2. In this lecture, we will talk about Kuhn-Tucker conditions. So, in previous lectures, we have talked about equality constant optimization problems. We have also talked about inequality constant optimization problems. So, optimality criteria for equality constant optimization problems and inequality constant optimization problems we have talked about under the framework of Lagrange multiplier techniques. So, we will see today that when you combine these two, what you get is known as Karush-Kuhn-Tucker condition or Kuhn-Tucker condition or KKT condition, sometimes also known as KT conditions. So, this is the form of the nonlinear programming problems or general problems with both equality and equality constants we are considering. So, we are considering minimization of a function, n variable function subject to p inequality constants which are of less or equal to type and m equality constants. As we have discussed before that if you have inequality constant of type greater or equal to, you can always convert it to less or equal to type. So, this is the form that we are using. It is not necessary that you have to stick to such formulation, but we are doing this in this lecture or in this course as a convention. So, let us quickly review what we have learned about the optimality conditions for equality constraint optimization problems and inequality constraint optimization problems. So, I have an equality constant optimization problem, minimization of f(x) n variable function subject to m equality constant h j equal to 0, where j goes from 1 to m. So, the first thing we did is we formulated the Lagrangian. So, Lagrangian can be formulated by multiplying each equality constant with its associated Lagrange multiplier and then add them up and also add this sum to the function value, given function f x. So, after we have formulated the Lagrangian, the necessary conditions are given as del L del x I equal to 0 and del L del lambda j equal to 0. Note that when you take del L del lambda j, you basically get back the equality constants. Now, about inequality constant optimization problems. So, we had n variable objective function subject to p inequality constants of less or equal to type. Again we formulate the Lagrangian. So, this time what we do is we convert the inequality constants to an equality constant by introducing a slack variable. A positive slack variable or non-negative slack variable greater or equal to 0 sigma square. Then the necessary conditions can be obtained as del L del x I equal to 0, then g j less or equal to 0, lambda j g j equal to 0, lambda j greater or equal to 0. So, if we sum up these necessary conditions, we get Karush-Kuhn-Tucker conditions, KKT conditions. So, now let us look at a problem with n objective functions, p inequality constants and m equality constants. So, define the Lagrangian. So, to define the Lagrangian, what we do is we define p Lagrange multipliers for each inequality constants uj. Similarly, we define m Lagrange multiplier for each of the m equality constants as V I. So, uj and V I are the Lagrange multipliers. So, then you formulate the Lagrangian function as f x plus V I h I summed over all I equal to 1 to m plus u j g j summed over all j equal to 1 to p, which can also be written as vector notation like this. Now, consider the gradient condition. So, del L del x I is equal to 0. So, del L del x I equal to 0 at stationary point. The stationary point is x star. Lagrangian is a function of x, u and v. X are the decision variables, u are Lagrange multipliers for inequality constant and v are the Lagrange multipliers for equality constants. So, the stationary point, let us say x star, u star, v star. So, del L del x I equal to 1 to n for each decision variables, del L del x I will be equal to 0 when evaluated at x star, u star, v star. So, this the gradient condition which must be satisfied. Then we need to check the feasibility. The stationary point must satisfy the inequality constant g less or equal to 0. So, all p inequality constant g j less or equal to 0, j equal to 1 to p must be satisfied. Similarly, all equality constants, we have m equality constants must be satisfied. So, this gives us the feasibility check. The stationary point must satisfy all inequality constant as well as equality constants. Otherwise, it cannot be a stationary point or a likely candidate for minimum. Next, switching condition. You remember the alternate form of the inequality constant optimization problem that we have discussed in the previous class. So, switching condition is obtained at u j g j equal to 0. So, either u equal to 0 or g equal to 0. G equal to 0 means the inequality constant g less or equal to 0 is being satisfied as g equal to 0, that means active constant. So, for active constant the u may be greater or equal to 0. When u equal to 0, g is less than 0, g is satisfied as less than 0, that means g is inactive constant. So, for inactive constant u equal to 0, Lagrange multiplier equal to 0. For active constant the Lagrange multiplier may be greater or equal to 0. So, non-negativity of Lagrange multipliers for inequalities, u is greater or equal to 0, all u's will be greater or equal to 0, non-negativity of Lagrange multipliers for inequalities. We have discussed in our previous lecture why this happens. Finally, regularity check. The point x star must be a regular point. The gradients of active constants must be linearly dependent. That means, at the point x star, the gradients of all active constants must be linearly dependent. Then only the point x star is a regular point, and KKT conditions will apply only for regular points. So, if you look at, we have basically combined the optimality criteria for equality constant optimization problem and the alternate form that we talked about for the inequality constant optimization problem. So, we first formulate the Lagrangian function, then the gradient condition del L del x I equal to 0, then you check feasibility, all inequality constant and equality constant must be satisfied. The switching condition must be satisfied, uj gj equal to 0 for all inequality constant. Lagrange multipliers for inequality constant must be greater or equal to 0, that means they must be non-negative, and the stationary point must be a regular point. That means, at stationary point the gradients of all active constants must be linearly independent. So, now let us formally talk about the theorem. Consider a general nonlinear programming problem which we call NLP problem, nonlinear programming problem. So, you have an objective function f x with n variables, x is n vector, you have p inequality constant less or equal to type, and you have m equality constants. Let x star be a regular point and the local minimum for the given nonlinear programming problem. Then there exists Lagrange multiplier v star and u star such that the Lagrangian function L is a stationary point with respect to x, v and u at the point x star. So, if x star is a regular point and the local minimum for the given NLP problem, then there must exist m Lagrange multipliers v star and p Lagrange multipliers u star such that the Lagrangian function L is stationary with respect to x, v and u at the point x star. So, for x star to be stationary, the conditions that must be satisfied are the gradient condition, inequality, equality, feasibility, switching condition and non-negativity of the Lagrange multipliers associated with the inequality constants. So, this is a formal statement of the KKT conditions or KKT theorem. So, first you define the Lagrangian function, take the derivative of the Lagrange function with respect to each decision variable, set them equal to 0, check for inequality constant feasibility, check for equality constant feasibility, check for switching conditions, which means the product of the inequality constants and its associated multipliers are equal to 0, and look for non-negativity, restrictions on Lagrange multipliers associated with inequality constants. There are few important observations about KKT conditions. The KKT conditions are first order necessary conditions for optimality. It means that if a point does not satisfy KKT condition, it cannot be optimal point. But the satisfaction of KKT condition does not guarantee optimality. So, it is a first order necessary condition. The points satisfying KKT conditions are called KKT points. The KKT conditions are not applicable at the points that are not regular. So, regular points means that the gradients of the constants will be linearly independent. At irregular points, the use of KKT conditions may yield candidate minimum points, but the Lagrange multipliers associated with the constants may not be unique. So, the KKT conditions are not applicable at the points that are not regular. KKT conditions are applicable only for regular points. Any point that does not satisfy the KKT conditions cannot be a local minimum or maximum unless it is an irregular point. Note that KKT conditions are not applicable for irregular points. So, now let us try to understand the geometric interpretation of KKT conditions. So, this must be satisfied at stationary point. Consider the figure. There are contours of the objective functions. We are minimizing a function and x is the minimum point. There are three constants g1, g2 and g3. Note that at the optimal point x, the constants g1 and the constants g2 are satisfied as active constants. So, at the optimal point x, the constants g1 and g2 are active, whereas g3 is not active, g3 is inactive. So, at the optimal point, only the active constants are important. Now, we know that the gradient of the constants will be tangent on the point of the constant surface. So, del G1 is tangent here. Similarly, del G2 is tangent here. Now, if you look at this statement or this expression, what it means is that the negative gradient of the objective function is a sum of or non-negative sum of the gradient of the active constants. So, G1 and G2 are the active constants, and if you can easily show that the negative gradient is basically this diagram, this the drawing was not correct, but if you draw it correctly, you can easily show that the negative of the gradient of the objective function is the sum of the gradients of the active constants. You can also say the negative of the gradient is contained in the cone created by the gradients of the active constants. Note that we are minimizing a function and the function value increases in this direction. So, the gradient of the objective function points in this direction. So, the geometric interpretation of the KKT conditions is as follows. The negative gradient of the objective function can be written as a non-negative sum of the gradient of the active constants. Note that the inactive constant as shown by G3 here has no role at the optimal point. Now, let us talk about second order necessary conditions. The KKT conditions were, as discussed as of now, were first order necessary conditions. So, now let us talk about second order necessary condition. Let X star satisfy the KKT conditions for the general nonlinear programming problem. You define the Hessian of the Lagrange function L at X star as del grad square L equal to grad square f, the Hessian f, for the equality constants and for the inequality constants. So, this is how we define the Hessian of the Lagrange function L. So, let there be non-zero feasible directions d not equal to 0, which satisfy the linear systems as shown at point x star. That means, these linear systems, the gradient of equality constants times the feasible directions d. So, that will give m linear equations. So, grad h d equal to 0 for all m equality constants. Also, for all active inequalities, that means where the inequality constants are satisfied as g equal to 0, for all active inequalities, the grad g times d equal to 0. So, let there be non-zero feasible direction d that satisfy these linear systems. Then, for x star to be a local minimum, it must be true that the quantity d transpose Hessian of L times d is greater or equal to 0. Note that this is a quadratic. So, the second order necessary conditions are as follows. You first define the Hessian of the Lagrange function L at x star. Let there be non-zero feasible direction D which satisfy grad H times D equal to 0 and grad G times D equal to 0 for active inequalities which are satisfied as G equal to 0. Then for x star to be a local minimum, it must be true that the quadratic Q defined as D transpose Hessian into D transpose is less or equal to 0. This is second order necessary conditions. Again, this is second order necessary condition. Satisfaction of these may lead to a local minimum, but not guaranteed yet. So, the minimum point will be guaranteed if it satisfies second order sufficient condition. So, let x star satisfy the KKT conditions for the general nonlinear programming problem. Again, define the Hessian of the Lagrangian as we have done in the previous slide. Let there be non-zero feasible directions D which satisfy the linear systems that we have talked about in the previous slide. That means gradient H times D equal to 0 for all equality constants, grad G times D equal to 0 for all active inequalities which are satisfied as G equal to 0, and grad G times D less or equal to 0 for those active inequalities with U equal to 0. Then x star is a local minimum if the quadratic D transpose Hessian times D evaluated at x star is strictly greater than 0. This is second order sufficient condition. So, when you compare with the second order necessary condition, you have an additional restriction on these inequality constants, and then the quadratic has to be strictly greater than 0. So, this is second order sufficient condition. Now, let us talk about KKT conditions and convexity or KKT conditions and convex problems. If x star is the local minimum for a convex function f x that is defined on a convex feasible set S, then it is also a global minimum. If both the objective function and the feasible region are convex, then the NLP problem is a convex problem. So, remember, if both the objective function and all the constraints are convex, then the NLP problem is a convex problem. In other words, we can say that if the objective function is convex and the feasible region is also convex, then the given problem is a convex problem. For a convex problem, we are assured that a global minimum exists and that any point x star that satisfies the first order KKT conditions will be a global minimum. So, for a convex problem, the first order necessary KKT conditions also becomes sufficient conditions for global minimum. Note that a linear programming problem, the objective function is linear, all the constants are also linear. So, this is a convex problem. So, you are assured that a global minimum will exist for a linear programming problem. Now, let us take a simple example for KKT conditions. F equal to x 1 square minus x 2. We have inequality constant x 1 minus 1 greater or equal to 0 Another inequality constant 30 minus x 1 square minus x 2 square greater or equal to 0, one equality constant x 1 plus x 2 minus 6 equal to 0. First, let us write this equation as where we have all the inequalities as less or equal to type. So, you can do that by simply multiplying the inequality constants by minus 1. So, we first write this in the form where inequality constants are less or equal to 0 type. Then define the Lagrangian function. So, we define two Lagrange multipliers E1 and E2 for G1 and G2 respectively, and for one equality constant I have one Lagrange multiplier V. So, you have del L del x1 equal to 0 and del L del x2 equal to 0. These two conditions gives these two equations. These are feasibility. So, this was del L del xi equal to 0. This is feasibility, which gives 1 minus x 1 less or equal to 0, x 1 square plus x 2 square minus 30 less or equal to 0, and x 1 plus x 2 minus 6 equal to 0. Then you have the switching conditions, which says u j g j equal to 0, and then you have u greater or equal to 0, u j greater or equal to 0 for inequality constants, and you know for Lagrange multipliers associated with the equality constants, there is no restriction on sign. So, V is free in sign. So, these are the KKT conditions. So, these are the KKT conditions. So, these conditions has to be solved, and then you can find out x 1 x 2 u 1 u 2 V. X 1 x 2 will be stationary point if it satisfies all these conditions. With this, we stop lecture 19 here.